Hello everyone, my name is Anvita Bansal and we are back with another lecture based on matrix. So let's have a look at the problem statement. Let me just check if you guys are able to see me. Fine, it works. Okay, so the problem for today is search in a row column sorted matrix. You are given a matrix of size n cross m where every row and column is sorted in increasing order and a number x. Find whether element x is present in the matrix or not. So you have to return true or false if this number x is present in the matrix. What is special about this matrix? That each row and each column is sorted on their own. Okay, each individual row, if you go and see, it is sorted. Each individual column will be sorted, okay, in increasing order. So how can you solve this problem? It's a very easy problem, just a simple intuition. If you get that, the problem is very simple, and I don't think so that will be really difficult for you to think of. So let's have a look. What do you think? Let's assume 62. Let's start with 62. Okay, we want to search for 62. How can you search in this matrix? Just think a little hard. So we know that each column and each row is sorted. Take some time to think about it. Meanwhile, let me just take this test case and then I shall discuss how can we solve this problem. Okay. So the brute force approach can be that you traverse over the entire matrix. You traverse over the entire matrix in two loops, two for loops, one for each row, right? And for each row, you are traversing and checking each element one by one. And for each row, what you are doing, you are going in every column. For every column in every row. So this typically becomes on square of on cross m of time complexity. So how do you check? It's a very simple brute force approach. You go and check each element. You know how to traverse a 2D matrix. It's a 2D grid. You know how to traverse it. We will traverse it using two for loops and put a check. If that current element, that will be, let's say, matrix of ij, is equal to x, then I return true. Otherwise, you keep checking, and in the end, if you might not have returned true, you will return false, right? So this is the brute force approach, and it takes on into m of time complexity, where n is the number of rows and m is the number of rows is n and m is the number of columns, right? Here it is 3, right? So what can you think of to optimize this approach so that it takes less than on into m time complexity? So let's have a look here. In this problem, see, what are we doing is, what we are checking, let's start a check from the topmost right element. What is a topmost right element? That means I'm talking about this particular element. I am choosing this element and checking. My current element that I want to check here is the element 62, right? So I go and ask, is 62 equal to this present value? But no, 62 is greater than 38. So from this, you can take a decision that one thing is for sure, I chose 38, that is the topmost and the rightmost element in this matrix. This makes one thing for sure, that if I go behind 38 in the same row, then I am going to get elements which are less than 38, right? And what if I go in the column just below it? I know one thing for sure, that I am going to get elements that are greater than 38. Does this make sense? If I am choosing any element which is present at this position, then the corresponding row will have this element as its maximum, and the corresponding column will have this element as its minimum of column. This element will be minimum of its column and maximum of its row. So this can help you take a decision on how to traverse in order to find 62. So if you go in this row backwards, you are definitely not going to get 62. There is a possibility that you may get 62 in its corresponding column, right? So if you choose to take this column to search your answer, then this might return you the answer. Still not necessarily that 62 will be present here, but here it is sure that we can eliminate this row for our search. So this is basically what we are discussing is elimination method, not something that is explicitly defined that this is some kind of a method, no, but approach that we are using here is a elimination approach. Okay, now you come in this column. When you come in this column, you check for the next element in that column, which is 60. So when you check for 60, you see that it is less than 60. So if you go in the column of 60 further, one thing is sure that you are going to get elements that are greater than 60, right? And 62 is obviously greater than 60. So is it a wise thing to go into and search in the same column or search in its row? Obviously not. We can eliminate row and keep our search continued for the particular column. Now we are at 69. So we know 62 is less than 69. So it will be advisable for us that we do not go further into its column because elements will be greater than 69. So if I want to check if I can have something less than smaller than 69, then that would be its corresponding row. So this time, although I do not have further elements to eliminate in this column, but one thing is sure that even if I have 62 in this matrix, then I am not going to get in its column, but there might be a possibility I get in its row. So this time I am eliminating column and going in its row. So when I go in its row, I will just simply decrement the count of j, which I am using to iterate over the columns, right? So this column, right now I will go and search for this particular column and this row, right? So I am at 51 now. One thing is for sure, for element greater than 51, I need to go down in its column. And if I want to check an element less than 51, I will go back in its row. But here, if I go back, obviously that is not advisable, but because 62 is greater than 51. So obviously if I might find 62, that would be in its corresponding column. But I check that this is the end of this column. I cannot go further down in this column. So that means I have iterated over all the possible values of my search, and 62 is not present in this matrix. So finally it will return me false. So what are you doing here? You are typically checking, you are initializing your, let me tell you what we are doing. If I were to write a pseudocode, so you are checking it in such a way. Let's say I am initializing int I, which is the row which you are taking in order to start your comparison. So you are starting with this element. So this element belongs to which row? Row 0. So I will traverse over the rows using I. So this is traversing over the rows. And let's declare another variable int j, which will traverse over the columns. And for our search, we are starting our search from the last column. So let's initialize j to m minus 1. Let's take n as the number of rows. Understand this thing, okay? And m is number of columns. Fine. So since I am starting my search with the extreme right and extreme topmost element, for that I am initializing these two variables as I starting from 0 and j starting from the last column. Okay, fine. Now let's keep a check. The check would be like this. Let me write this pseudocode here only so that you can have a look at the test case also simultaneously. So what am I doing is that while, since you are traversing your row from the 0th index, the last index that your row can go will be till n minus 1. And you are starting your column from already m minus 1. So the last index of your iteration for column can be 0. So you have to make sure that your I is less than n and your j is greater than or equal to 0, right? This is because you have initialized them in this way. Then what you are doing, you are checking the element we have chosen is this element. If matrix of ij, matrix or grid or whatever they have given this 2D array is exactly equal to x, then what, you simply return true, right? Otherwise, what can be the case? Either you eliminate the row for your search or you eliminate the column for your search. So what will be the cases of elimination? Let's take, this is the first case, when you get equal same element, then you return true. The second case can be that that particular element, else if your matrix of ij, either it can be greater or it can be less than x. If it is greater than x, right, that means this element is greater than x. It means that you want to search for x in that particular cell, or whatever column or row where you can get elements which are less than this value. So you should eliminate the column in that case. For example, let's say, for example, why I'm writing so, see, this is the case. For example, this was something like this, 338, and let it be, wait, let me create a test case, 330, and let me take an element which is greater than 62. Let it be 64. Okay, then the corresponding elements will be greater only. Let it be 65, let it be 69, this is 43, and rest are same. Okay, this is also one valid test case that we can take. Okay, so in this case, what I'm telling you is that there might be a condition where you are starting from this element, right, and the element you want to search is 62. So when this element came out to be greater than the element you are searching, this means if you go further in its column, you are not going to get 62 because all the elements will be greater than 64. So in that case, eliminate your column. So if you are eliminating your column, you are searching for the same row behind it, all the cells that are behind that cell in the same row. So in that case, you should decrement the count of j. That is, you are searching for every element in that row but the columns which are before that particular column. So what was this column? This is 0th column, this is first column, this is second column. So if you are at second column and let's say row is 0, so for 0 row, now you will be searching for 0 1, then you will be searching for 0 0 if you find that element. So if this is the condition, then you should eliminate column and search in that row for the previous column. So you will decrement the count of j. And in the else case will be this case in which the element is smaller than the element you are searching. So if you go behind it, you are not going to get. So you eliminate row. In that case, you should search in the corresponding column. For that, your I should be incremented. I was 0, now you check for I1 and the same column, whichever it is. Then I2 if you find that element. So you increment the count of I. That's how we are doing. Let's move to the code and write it. By that time, let me know if you guys have any doubt here. Okay. So let me tell you, binary search algorithm will not typically work here. I'll tell you why. You'll have to struggle a bit more if you want to apply binary search. The reason being, on what elements are you going to apply binary search? If you check for this element, if you check for this matrix, okay, let's say you want to apply binary search. What will happen is, you apply binary search on this particular row or any particular column only. Then how many times are you going to apply this binary search, and how will you maintain that now the next binary search will be on which number? Because see, binary search would be the best option if this was also ensured in this problem that rows are individually sorted, columns are individually sorted, but the next element, let's say this ends at 38, if this element, the next element of this row should be greater than 38, then we could have said that all the elements were in sorted order if we take it in a linear array form. You getting? Let me show you one test case where binary search would work, but here it won't. The reason is, I'll tell you. Let's say this is 1 2 5 and then we have 7. This is let it be this 6, 8, 12. Okay, and then this, let it be now the next element should be greater than 12 only. 15, let this be 21, let this be 30. Okay, now you see we are satisfying three things here, that your array is individually, each row is individually sorted, right, and each column is also individually sorted. If you check 2855, so in this case the third thing that we are satisfying is, whenever you end one row, the next starting element of the next row should also be greater than the previous element of the previous row. See, this was 12, this was 15, because in that way, if you consider all the elements, let's assume they were the part of one single array, so in that case they would have been a list of a sorted array 1 to 5. Normal traversal on matrix comes out to be like this. If I ask you to print the elements of a matrix, then you will iterate over each row and column simultaneously. For every row you are going to every column and printing. So for next row, the next element would be 6 followed by 8, then 12. So if you visualize them as part of one single array, single 1D array, then you can apply binary search on this single array and you start your low from here, high from here, mid would be somewhere here, and then you start your binary search. Also you will have to manipulate your indices here for a single, not that you are going to create another space of a single 1D array. You have to visualize it, you have to handle this thing with the help of indices that you have. So if this is 0 0, this is 0 1, this is 0 2, you can visualize them as 0 1 2 3 4 5 6 like that, and then you manipulate them in such a way that whatever it is, for let's say this is 0 1 2, so 2 divided by what is the length of this number of rows, 2 divided by 3, 2 remainder 3. So 2 divided by 3 is 0, remainder is 2. So what is 0 comma 2? 1 0 1 2, 0th row and second column 0 1 2. So this comes out to be 5. You getting this thing? See, if in a 1D array you are taking an index, some indexes idx, okay, and you want to know that index corresponds to what row and column index in your matrix. So what you can do is, you can simply do idx divided by what is the number of row 3, and idx remainder that number of how many columns 3. So that will give you 2 by 3 is 0 and 2 remainder 3 is 2. This 0 comma 2 gives you row and columns index. So this is one thing you can do, but this will not be applicable in this test case for this problem statement at Geeks for Geeks. The reason being, if you see the next element of this row, it is not greater than the previous element of the previous row. So you cannot ensure that all the elements can form a one single array of sorted elements on which you can apply binary search. You can apply binary search individually on each row like this, or each column from here till bottom, but is it going to help you? It is going to complicate only your search. That is why we are not using binary search here. So I hope this thing is clear to you. Great. Fine. So in fact I'd say rather it's a simple problem only. Binary search, thinking about binary search is great. If you got an intuition, then obviously that approach is also very easy, and in this problem also, see, the code is very easy. Again, it's just that you need to think that why we are starting from here and how we are handling the use of elimination here. That's all. Okay, so let's initialize int I. The row is starting from 0 and a j is starting from the last column, which is m minus 1, equal to m minus 1. So while your I is less than n, right, and your j is greater than or equal to 0, right, that's what you want to do. You go ahead and check if your matrix of ij is equal to x, return true. Else if matrix of ij is less than x, Okay, if it is less than x, that means this value is less than x, so you're not going to get it in the same row. Eliminate the row and search for the column. So in order to search for the column, you keep the column j index same and increment the count of rows index, right? So in that case, j was whatever j was, j will remain same, but your I will increment, I plus plus. In the else case, your j will be incremented. In that case, where let's say this was 67, so you might find 62 in this row behind, so I will remain constant and you will just decrement the count of your column index. So that is why we are doing j minus minus. And once you come out of this loop, you return what? False. So this method typically it is close to n cross m only, although it is not exactly n into m of time complexity. So but it is a bit less than that. Obviously not that we are optimizing with a great difference, but obviously this is not for, as you can see, it's not taking o n into m of time complexity, right? So it kind of takes 2 to the power something of time complexity. So that's all about this problem. If you have any doubts, you can ask me. Let me check if you guys. Fine, if you have no doubts, we can wrap it up. Otherwise, that is all for today. Let me. So, shall we wind it up? Okay, guys, then see you all in the next lecture. Thank you, everyone. Bye bye.